All right, welcome to percent yield, mass percent by composition, and excess and limiting reactants. I've got a couple examples I'm going to do for each type, but you will have to get out a piece of paper and title it with the same title, put your name. This is actually going to be due of 512, so 512 in class. Please make sure you put your period on there. All you have to do is questions 1 through 10. Okay, you don't have to copy my examples if you don't want to, and the worksheet is posted online in Teams. Okay, so a couple things you're going to need. You're going to obviously need the periodic table if we're talking about mass percent. You're going to need a calculator or your phone to do the calculations. So let's get right into it. Mass percent composition is the percent of mass in each element of a compound. So I've got the little formula here for you. So I'm going to kind of zoom this in so you can see the examples. So percent by mass is the mass of the element, we're assuming in 1 mole of what we're given, by the molar mass of the compound. Now the compound could also be a solution, but it's pretty much the same thing. The individual mass divided by the whole mass. So part divided by whole times 100. Pretty easy. So the example is H2O. Well, we know that the molar mass of H2O, total mass, is 18.02 grams per mole. We know that because we take 16. The oxygen times 1 is only 16 grams, and the hydrogen times 2 is 2.02 grams. We add that up, we get that. Well, percent by mass is taking the individual mass divided by the whole times 100. So hydrogen is 2.02 divided by 18.02 grams times 100. Grams cancel. That's why percents, they don't per se have a unit, they have the percent sign. So 2.02 divided by 18.02 times 100. Now, percents typically are always 2 past the decimal. That's like the general rule. So we got 11.2097, yada, yada, yada. So we're going to round that to 11.21%. Now, 16 divided by 18.02. So I'm going to put oxygen here. 16.00 grams divided by 18.02 grams times 100 divided by, grams cancel, and we get, forgot to do times by. Times by 100 is 88.7902, yada, yada, yada. So we're going to round that, 88.79%. Now, if you only have 2 elements, let's look at this. It's part divided by whole, so the whole has to be 100%, right? So if I take 100 and subtract 11.21, I get 88.79, which is what I got here. Now that kind of only works if you have 2 elements. If you have 3 elements, you can find the percent composition by mass of 2 of them, and then that total minus 100 would give you the third. Okay, so these 2% or 3% or even 4 if there's 4 elements should always add up to 100%. If you rounded wrong, you might get 100.01 or 99.99. So just bear in mind, watch your rounding. The percent should add up to 100. Okay. So what's different between percent mass by composition and percent yield? Well, percent yield is talking about actual yield in an experiment, like what you actually got, versus what you should have got, the theoretical yield. It's not part divided by whole per se. It's you do an experiment, you got this amount of mass, you should have gotten this mass, you divide those two, and that tells you like how accurate you are. So we kind of did this with the nail lab. You were doing a ratio, trying to figure out moles of copper to moles of iron to figure out, did you have an iron 3 nail or iron 2? If your actual yield was close enough to your theoretical, you should get 0.999. That means you had very little error. Okay, so let's look at the example. 2 moles of calcium carbonate are reacted, and the theoretical yield of CaO is 2 moles. So this is my theoretical yield. Okay, that's what I should have got. But the actual yield is 1.5. So what is the percent yield? So let's say I would have taken calcium carbonate and decomposed it. We would have got calcium oxide and calcium or carbon dioxide. So if I decompose this, and I'm supposed to get 2, but I only got 1.5, what amount of error, what was my actual percent yield? Well, we're taking the actual 1.5 mole divided by 2.0 mole times 100, and let's do that math. 1.5 divided by 2.0, moles cancel, and I get, oh, forgot to times it by 100. I get 75%. So what that means is that I got 75% of what I should have got, which means I had about roughly 25% error. Something happened here where I lost 25% of the product I should have got. Okay? All right, so I want you to use those 2 examples. Mass percent is, or mass percent of composition is 1 through 3, and then percent yield is 4, 5, and 6. Okay? All right, let's look at the back. Now, you're probably going to have to pull this up in teams to see the color. This green was supposed to be like a dark green, but it turned out it looked like black. So I used a highlighter. So you're going to need colors, because this one you can clearly see a size difference. This one you can clearly see a size difference. So I labeled the bigger atom as nitrogen, N2, and then these is H2. Here you got chlorine and hydrogen, so this one is H2 and this one is Cl2. Okay. Here we got cars to tires, or car body, so car body and tires. Okay. And then here, the smaller ones, it's kind of hard to tell, but you can kind of see a difference in size. The smaller ones are red and the bigger ones are green. This one we're just going to go by color, and then this one is labeled, where H2 is the little small filled in circle, O2 is the open bigger circle. Okay? So what is excess and limiting reactant? Well, it's just what it means. Excess reactant is the reactant that is not used up. We have it left over after the reaction. The limiting reactant, I also highlighted that, the reactant that runs out or that's used up. Okay? So looking at pictures, you just got to look what got used up and what didn't. And I just realized I didn't color in these 2 hydrogens. So let me do that real quick. So what got used up is the limiting, and what didn't get used up is the excess. So looking at this diagram, we got 1, 2, 3, 4, 5, 6 of the nitrogen molecules. And then we got 6 atoms. So we have 6 atoms of N, or 3 of N2. Then I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 atoms of the H, or 1, 2, 3, 4, 5, 6 molecules of H2. Okay? So when you're determining what the limiting and what the excess reactant is, you're really looking at the after box. Okay? So here we got 1, 2, 3, 4 atoms of the N that bonded with 3 atoms of hydrogen. Well, I have 12 atoms of hydrogen, so let's count them up. 3, 6, 9, 12. So it looks like all of the hydrogen got used up, and we have some nitrogen that's not bonded. So nitrogen is my excess reactant. or we just put ER. And then hydrogen, because it all got broken up and bonded to nitrogen, this is my limiting reactant, it's what I ran out of. And we just label that LR. Okay. So in determining excess and limiting, you're really looking at the after, but you need to count up how much you started with and look at, okay, well, what all got bonded up? Well, what all got bonded up was the hydrogen. What didn't get all bonded up was the nitrogen. So we had nitrogen left over. Okay. Now, if we were to write this as a balanced chemical reaction, we would say, well, we needed 2 of the N2 molecules, right? Because only 2 of them reacted, 2 N2, plus we needed all of these hydrogens, so 1, 2, 3, 4, 5, 6 H2, which produce 4 NH3s. Now we could reduce this because, you know, we got 2, 6, and 4, and 2 goes into all of them. So the correct balanced equation is 1 N2 plus 3 H2 makes 2 NH3. Okay. In a balanced chemical reaction, we don't put the excess reactant. It's understood that if it goes to the end and everything reacts, we will probably have some excess reactant, but it's not shown in the balanced chemical equation. So for 7, 8, 9, and 10, I want you to use the labels I gave you, okay, or colors. This one you're going to have to use colors. You don't have to give me the correct balance equation, but just tell me what the excess reactant is, what the limiting reactant is, what is excess, what didn't get used up, and the limiting, what did get used up in every single reaction here or scenario. Okay. All right, and that is your review on percent yield, percent mass by composition, excess, and limiting reactant.